We've got a massive problem in AI. Our models are just getting way too big. And the common sense solution, right, is to simplify, to flatten things out. But what if that's completely wrong? What if the real key to making AI smaller and faster and way more powerful isn't to reduce complexity, but to actually embrace it by adding more dimensions?
It all kind of starts with a puzzle. Look at this. This tiny board is an edge AI processor. It's designed to run these super powerful AI models without ever needing to connect to the cloud. But how? How can something so small handle models that we all know are famously huge? Well, the answer is this amazing trick of perspective, a mathematical concept called tensorization. So here's how we're going to break it down. First, we'll dig into the AI size problem and what I call the matrix trap of 2D thinking. Then we'll get to the good stuff, the tensor solution and the magic of decomposition. And finally, we'll look at why the future of AI is, well, multidimensional.
Okay, let's start with the problem itself. Data is just exploding, right? And our AI models are ballooning to try and keep up. Now that's totally fine for giant cloud servers, but it's a complete disaster for the everyday devices in our pockets in our homes, what we call the edge.
See, the real issue is that real-world data isn't flat. A video has a time dimension, brain signals have depth, social networks have all these complex links. But for decades, machine learning has taken all of this rich, beautiful data and just squashed it into flat 2D tables or matrices. It's kind of like taking a 3D sculpture and running it over with a steamroller. You just lose all the important structure and you end up with something that's huge and super inefficient.
And this, right here, is the matrix trap. By forcing everything into these simple rows and columns, we've basically been teaching our AI to see a rich, complex world in only 2 dimensions. And that's been limiting its true potential this whole time.
The core idea is actually pretty simple. A matrix, well, that's just a flat spreadsheet. It's got 2 dimensions, rows and columns. A tensor, though, think of a tensor like a Rubik's Cube. It has rows, columns, and depth. And it can go even further, with 4, 5, or even more dimensions. It's a container that's built to hold data's true, complex shape.
And once you start thinking this way, you realize we're literally surrounded by tensors. A color photo? That's a 3D tensor, height, width, and color. A video? That's a 4D tensor because you're adding time. Even a simple fact like Paris is the capital of France can be part of a giant 3D tensor of knowledge. Our world is just naturally tensor-shaped.
So, what's the solution to all this? Well, if flattening complex data is the problem, the answer is almost laughably simple. Just stop doing it. We need to embrace the complexity. We need to use tensors to work with data in its native, multi-dimensional form.
Tensor sounds like some super complex mathematical term, but really it's just a catch-all. A single number? That's a 0D tensor. A list of numbers? That's a 1D tensor. Our good old spreadsheet? That's a 2D tensor. And the Rubik's Cube? A 3D tensor. It's really just the word we use for data that has more than 2 dimensions of relationships.
Now here's the paradox, and this is where it gets really cool. You would think that more dimensions means more complexity, more data, slower processing. The famous curse of dimensionality. But as this research shows, the exact opposite happens. By preserving the data's natural structure, we end up creating models with fewer parameters that run faster. It's a massive, totally counterintuitive win.
So how does this magic actually work? The secret sauce isn't just using tensors. It's about breaking them down. This is the art of tensor decomposition. Think of it like this. In 2D, there's a technique that lets us take a complex image and break it down into just a few simple patterns, like a set of basic lines and shapes. So by storing only those basic patterns, we can recreate the whole original image without having to store every single pixel. We're basically finding the core ingredients.
Okay, now we can apply that exact same logic to a 3D tensor. A technique called CP decomposition does the very same thing, but in 3D. It takes our complex Rubik's Cube of data and finds the fundamental 3D building blocks that make it up. Again, all we're doing is finding the most essential components.
So at the end of the day, tensor decomposition is an incredibly powerful compression technique. It's kind of like taking a complex meal and reverse engineering the recipe. Instead of storing the entire finished dish, we just store a few core ingredients and the instructions. It takes up way less space, but lets us create the exact same result.
And here is the wow moment. This slide shows the real-world impact. On the left, you see what happened when researchers flattened video data into one giant, long line. To analyze it, they needed this huge map of all the relationships between the data points, and that map took up a staggering 189 gigabytes. But on the right, they kept the data in its natural 3D tensor shape. The memory needed for that?
Under 100 kilobytes. No, that's not a typo. By not flattening the data, the memory requirement shrank by a factor of nearly 2 million. We're talking about going from 189 gigabytes down to something that could fit on a floppy disk from the 90s. This is the power of working with the data's natural shape.
So this clearly isn't just a mathematical trick. It's an engineering revolution. This level of compression is what's finally allowing powerful AI to escape the data center and live on the devices all around us. And this has now become a repeatable engineering process. You start by shaping your data into a tensor. Then you build a model. You use decomposition to compress it down to its essential parts, and then you evaluate the result. It's a really clear path from massive data to a tiny, powerful AI model.
And this brings us full circle, right back to our original question. How does that tiny little chip do it? The answer is tensor decomposition, because inside that chip is a specialized piece of hardware, basically a tensor calculator, designed specifically to unpack and run these hyper-compressed models with incredible speed and efficiency. The benefits for deep learning are just astounding. Huge layers in neural networks can be replaced with these compact tensor formats, and you can get compression factors of 200,000 times or even more. This technique can even shrink today's massive language models, like transformers, by a factor of 8 with almost no loss in performance. It's incredible.
And this method consistently outperforms the older techniques. So take something like pruning, which is basically like snipping away less important parts of a neural network. For this Google Vision model, pruning got about 1.6x compression. But tensor decomposition, it more than doubled that, shrinking the model by nearly 4 times, while keeping its accuracy totally intact. It's not just an improvement, it's a genuine leap forward.
So, where does all this lead? Well, it points to a future where AI isn't just locked away in the cloud, but is all around us, embedded intelligently and efficiently right into the world.
All right, so here are the key takeaways. First, think in tensors. Preserve the real shape of your data. Second, use decomposition to unlock that incredible compression and speed. This is the 1-2 punch that lets us put really powerful AI on small, everyday devices, and that's going to revolutionize everything from medicine to how we talk to our phones.
Which leaves us with the final thought. We live in a world of staggering, beautiful, multidimensional complexity. So if we really want to build an artificial intelligence that can truly understand and interact with this world, maybe we first need to teach it to see the world as it truly is, not as a flat spreadsheet, but as the rich, interconnected tensor it's always been.